Okay. Hear me? Okay. Thanks a lot for this opportunity and for, well, remaining until the very last session of the conference. So this is work done in collaboration with Bartosz Regula. As you see, it deals with these two tasks, these fundamental two tasks in entanglement theory, which are on the one hand entanglement testing, which I will define in a second, and on the other hand entanglement distillation. And I would argue these are two equally important tasks, and we need to understand them very well. And it turns out they are very deeply connected. So, okay, there's a kind of profound connection between them, and I hope I will convince you that this is the case, and it's a worthwhile thing to try and explore it. Okay, so first of all, what is entanglement testing? Okay, so let's say you have a system that it's you're promised it's a bipartite system. It's either in an entangled state, rho AB, that is fully known to you, or in a generic separable state. Okay, and you want to know how efficiently you can decide between these two alternatives by testing. All right. Okay, so that's a scheme. That's kind of a basic drawing. So you have an unknown state, which could be either rho, which is known, or a generic separable state. And what you can do is you can implement a measurement. Okay, binary measurement to make a guess. So and then in the end you have to guess. Of course, so here this S stands for the set of separable states, so the set of convex halves of product states. And while M for now is just a capital M is just a generic set of measurements. Okay, we'll see some examples, some interesting examples in the next slide, but for now it's just generic. You know, it could represent what you can do in the lab. Okay, so, but okay, what are interesting sets of measurements? So first of all, there's a set of all measurements on a bipartite system. That's definitely a very interesting set. So you're assuming that Alice and Bob have kind of generic power. They can measure, they can do any measurement on their system. But of course, this is often not the case. So maybe you want to do instead, so Alice and Bob, maybe they have all-powerful quantum computer locally, but they can only communicate classically for some reason. So then the set of measurements that you would implement in this case is the set of LOCC implementable measurements, which we denote by LOCC, which I'm not defining mathematically because it's very complicated, but it's okay. Operation, it's very clear. And precisely because this is very difficult to characterize, we also need a relaxation, a kind of simplification of the set. And there is a standard candidate, which is the set of separable measurements. Whoops, okay. So separable measurements look like this. Okay, this looks complicated, but in practice, it means that every P of M operator has to be separable, okay? It's not a state, it's an operator, but somebody's partying really hard. Okay, right, so this is the set of inclusions. So LOCC is the smallest set. Then there is a set of separable measurements, and then the set of all measurements is much bigger. Okay, so that's a scheme. So there are two types of error you can make. There's a type 1 error, which is when the state was separable, but you think, the state was entangled, it was rho, but then you thought it was separable, okay? So you didn't recognize that the state was actually entangled, was actually rho. And then there's an opposite type of error, type 2 error. The state was actually separable, but you thought you got an entangled state. So, and I would argue that in many reasonable scenarios, this is actually the most serious type of error, because maybe you bought this device so it's been promised to you, produces an entangled state, and if you make this error, you have been falling for the scam, quantum scam, and you are given a separable state, and this might compromise the security of whatever quantum protocol you're running, cryptographic protocol you're running. So that's kind of that's the error we want to minimize in many interesting cases. And okay, so it looks like this. We introduced this beta epsilon m function. So this is the minimum overall measurements of the type 2 error probability for a given type 1 error probability. Of course, you have to constrain the type 1 error probability, otherwise everything trivializes. So if you can make the type 1 error probability equal to 1, of course, you will also have the type 2 error probability equal to 0, because there's a trade-off between the two. So by constraining it, we kind of we have a non-trivial function. Okay, so this is what it looks like mathematically, but it's very simple. It's just probability and the Born rule, basically. Okay, so far so good, right? The problem is that the way I think of quantum information theory, it's always like kind of a very dangerous chess game against a very powerful adversary, which is the asymptotic limit. Okay, it's a very powerful adversary in a chess game. Then I thought immediately of this movie, which is Seventh Seal. So if you haven't seen it, go watch it. It's much better than my talk. So anyway, this guy is Death. So and this guy, the main character, is playing a dangerous chess game, as you can guess. So this is us. So let's try to see what we can do. Okay, so we have a large number of IID copies of rho, right? So then what you expect is that the error, the type 2 error probability will decay exponentially, because the more copies you have, the better you are at discriminating them, okay? At discriminating them from separable states. And that's actually what happens. But the problem is that we want to compute the exponent. We want to know everything about this problem. And the exponent is very important because, of course, you want to know exactly the asymptotic decay. To predict how many copies you need to be reasonably sure that you are not falling for the quantum scam somehow. Okay, so in practice, this exponent is called the Stein exponent. This depends on the set of measurements you're using, of course. And it's given by this friendly-looking expression, I guess. So in practice, you should think of it like okay, this type 2 error probability minimized decays to 0 with n with this coefficient, which is just the Stein exponent. Okay, good. Right. So that's the expression. What is Sn there? The Sn there is the set of separable states over n copies of Alice and Bob. Okay, Alice's and Bob systems. But the important point to understand here is that these copies, they have to be, so the state has to be separable across the cut Alice versus Bob, but it can be very much entangled across the different Alices and the different Bobs. Because in practice, the situation looks like this. So the generic state will be kind of separable here. This is kind of blue classical correlation, I don't know. And but it can be very much entangled across the several copies. And this is kind of what, this is why this problem is difficult, basically. So again, we're kind of doomed if you try to solve this directly because of this n-body correlations. Okay, this the problem becomes very difficult. Okay, but let's look at the easiest case, right? The easiest case is when the set of all measurements is the one you can implement in the lab, right? So then you have all-powerful, even global, the power to do even global measurements on Alice and Bob. So that should help us, right? There is no solution for this one yet. So and as you know, this one is the problem of computing the Stein exponent for this problem when you have the set of all measurements. This is exactly the generalized quantum Stein's lemma that we heard about in the RAM session, for example. Most importantly, I would say the RAM session. So exactly, the conjecture is that this is equal to the regularized relative entropy of entanglement, which is given by this funny expression, in which we'll see also in the next slide, but you are trying to minimize kind of the relative entropy distance of from your state to the set of separable states, and you're normalizing it and taking the limit, the asymptotic limit. Okay. But it turns out that in this other case, in which your measurements are forced to be separable, for some mysterious reason, this case is actually easier, even though it looks more difficult because you are in a more constrained setting. For some reasons, it's actually easier. And it turns out that Brandao, Harrow, Lee, and Perez back in 2020, but I think the archive version is actually much older than this, computed the Stein exponent, and it's given by this expression. It looks very similar to this one, to the regularized relative entropy of entanglement, but there's the SEP measurement stage, which I will explain in a second what this does. Okay, let's try to understand these measures, right? Shall we? So the parent quantity is the relative entropy. Okay, the relative entropy is kind of the fundamental measure of statistical distance between quantum states, and is given by this expression in terms of two density matrices rho and sigma. So then if you want to compute the distance, so if you want to define an entanglement measure, with that, you could think of taking the second state to be separable and kind of finding the closest separable state to a given state rho. Okay, so kind of finding the distance from your state to the set of separable states as measured by the statistical distance. Okay, that's what if you do this, you define the relative entropy of entanglement, which is given by this expression. But then, so this was started long ago by Vedral and Plenio and Knight, I think, which I should have written the reference here. But then this guy, Marco Piani, comes along and says, no, let's do something else first. Let's introduce a further stage, a measurement stage, in which we kind of, before computing the relative entropy, we measure both states with a separable measurement. Okay, why would you do this? This looks unnecessarily complicated, I would say. And in fact, this is what I thought for a long time. This is it's kind of very contrived. And then, he keeps on. And he goes on and defines also the regularized version of this, so in which you take many copies of your state. Okay, this is even more complicated. So why are we doing this? This looks very contrived, somewhat. This is what I thought. But then it turns out that this quantity actually behaves much better than the relative entropy, the standard relative entropy of entanglement in some respects. Okay. For example, it obeys a crucial property that's very useful in several cases, which is strong superadditivity, meaning that if you compute the entanglement of a state, of a four-partite state, Alice, Alice prime, Bob, Bob prime, with respect to this measure, see this is an entanglement measure, then the entanglement content of this four-partite state turns out to be larger than the sum of the two entanglement contents of the first state on Alice Bob and the second state, the reduced state on Alice prime, Bob prime. Okay, this is a very useful property that is shared by like just a handful of entanglement measures. Okay, and this is one of the reasons why they could compute the Stein exponent over here. Okay, so it seems more complicated, but turns out that it's actually easier to manipulate several times. Okay, so this is the picture of me with Marco Piani. I was very happy to meet him finally. This is, I think we are having dinner in Waterloo. I'm very enthusiastic about this Piani quantity, as you can guess. Okay, so but now I have talked about the kind of entanglement testing side of this picture. Let's cross the bridge and go to entanglement distillation, shall we? Okay, so what is entanglement distillation? It's the task of manipulating a certain number of copies of rho and transforming them into copies of the EBIT, okay, the maximum entangled 2-qubit state. Okay, and so the way we do this is by applying some operations in some class of free operations F that I won't specify for now. And then, okay, we aim to obtain a state that is asymptotically close to a certain number of EBITs, and the number of EBITs we get out of this process per copy of rho, in this case it would be 2/3. That's the rate of the achievable rate of the entanglement distillation protocol, and the supremum of all achievable rates, that's the distillable entanglement under operations in F. This crucially depends on the operations in F and of course on the state rho. But okay, but what free operations can we use? So okay, there is a standard answer, kind of bottom-up constructive, which is of course LOCCs, local operations and classical communication. That's all you can use in a physically reasonable setting, I guess, at least with standard quantum mechanics. That's what you get. This is, of course, it's a very reasonable answer, a very good answer, well motivated, but there are a couple of problems with this. One is that it's an extremely difficult quantity to compute, this distillable entanglement under LOCC. In fact, we have basically 0 formulas for that. We have several bounds, but especially the upper bounds oftentimes are not tight. There are certain states that we suspect are bound entangled, so 0 distillable entanglement, but we can't prove them because we can't prove this because we don't have good upper bounds. Okay, so this is the first problem. The second problem, kind of more philosophical, kind of more from the perspective of comparison between entanglement theory and thermodynamics, is that the theory that you get in this way is irreversible. Okay, and I will refer you to the talk by Bartosz on Tuesday, I think. For that, so that the theory that you get is irreversible, so and that's kind of also undesirable from the point of view of axiomatic treatment of entanglement theory. Okay, so and you don't get a single entanglement measure because of this irreversibility, so that's also somewhat undesirable. And it turns out that both of these problems can be solved if we go beyond LOCC. Okay, so but stay with me for a second. What does this mean? Let's say we take a simplified approach. Instead of bottom-up, we take a top-down axiomatic approach. Instead of saying, okay, F can do this and this, let's say what F cannot do. Okay, so let's give some axioms on what the free operations cannot do. And there are two advantages to this. Is that the first one is that this gives bound on the power of LOCC. So you get an upper bound on the power of LOCC by going to instead this set F, which will be larger, typically than LOCC. And if you can compute this new quantity, you get an upper bound on the distillable entanglement at the LOCC. So even if you don't care about these free operations, because I don't know, whatever, you don't care about this comparison with thermodynamics, this should still be very interesting to you because it's a very good way to find bounds. And historically, many of the bounds have been found in this way, more or less consciously. So, and the other thing is that if the generalized quantum Stein's lemma holds, then this approach also gives you a consistent with some quotation marks, and reversible theory of entanglement manipulation. Okay, I won't go into this, but it's kind of just to tell you that this going beyond LOCC paradigm is really can address a lot of problems. Okay, so the way you should think of it is like this axiomatic entanglement distillation is a bit like the query complexity of entanglement theory. Okay, So it's not like maybe its physical justification is not does not take into account every cost that you incur by implementing a quantum algorithm, but it's a very useful tool to bound things, basically. Even if you don't care about, I mean, there's more to it than this, but even if you don't care about it, that's at least this. Okay. Good. So what axioms should we impose? So the first axiom is that operations in F, free operations should not be entangling, should be non-entangling. So they should send separable states into separable states. Okay, so this is good, but this is a Schrödinger picture. What about the Heisenberg picture? You could also say also the adjoint. So the adjoint action in the Heisenberg picture should be non-entangling because it should send separable measurements into separable measurements. Otherwise, it's not. This is also a very reasonable axiom. And if you combine these two axioms, you get a set of operations that is called the set of dually non-entangling operations. Okay. So this is the picture for those of you who really like this different classes of operations. This is a set of LOCC. This is kind of the smallest. Then this is generalization to PPT. And then there are different extensions to this DNE class, which is this red circle and ellipse, and this non-entangling, which is even larger. Non-entangling is the operations that obey just the first axiom. Okay. Good. So in this talk, we're going to work with this DNE set. Okay, so I promised to you a correspondence between this Stein exponents and entanglement distillation. So there you go. So first row is Stein exponents. This one we don't know. This one is the regularized Piani, relative entropy of entanglement. And here I put the distillable entanglement. Okay, so I claim that these Stein exponents are equal to distillable entanglement. Distillable entanglements, I guess, under different sets of free operations. Okay, so the first. This was proven by Brandao and Plenio. This is not affected by the issue. The fact that the distillable entanglement under non-entangling is actually equal to the Stein exponent when you take all measurements. We don't know how to compute it, but it's nevertheless equal to that one. So if we could solve the GQSL, you could also prove that this is equal to the regularized relative entropy of entanglement. Okay. And now our main result is okay. So first of all, this is surprising because it's a connection between the Stein coefficients and the word of axiomatic entanglement distillation. And this was, I think, conceptually one of the nicest things about this paper by Fernando Brandao and Martin Plenio. But then you could also ask yourself, okay, what happens to this bottom right corner of this table? And it turns out that, okay, so you can solve also this one. So this Stein exponent is equal to the distillable entanglement under DNE operations, okay? And the fact that there is this dual constraint reflects into the fact that you have this separable measurement stage somehow. These two things are very much connected, because a separable measurement is kind of separable at the dual level, right? So, okay, this is our first main result. So in particular, this gives you a regularized formula for the distillable entanglement under some class of operations, right? This DNE, and this is only the second class of free operations for which we have a formula, a regularized formula, but still a formula for the distillable entanglement after the set of one-way LOCCs. Set of one-way LOCCs was solved by Devetak and Winter in this paper 2005. They also have a regularized formula, so both their formula and our formula are somewhat difficult to compute in general because they involve a regularization. But there are things you can say without computing them that you could not before this theorem. Okay, so you can attempt to estimate them by using the regularized formula in several different senses. So okay, so this is kind of why we liked a lot this result. It's this formula, closed formulas for the distillable entanglement do not come by every day, basically. Very difficult. And it also shows that there is no bound entanglement under DNE. So because this quantity turns out this is faithful, it's non-zero for every entangled state. Good. Okay, but so there's another question that we want to answer, which is, does the restriction, so if you restrict yourself from set of all measurements to just separable measurements, does this affect entanglement testing asymptotically? Does this worsen the quality of entanglement testing? So you could ask yourself, does there exist a state for which the Stein exponents, so there's a gap between the two Stein exponents, so the Stein exponent with all measurements is larger? Is that true? So so let's study. There's a natural candidate, I think, which is the universal counterexample in entanglement theory, and that is called the antisymmetric state. This is just a normalized projector onto the antisymmetric subspace. this has been studied by Cristandol, Schuch, and Winter in 2012. And what they proved is that the regularized relative entropy of entanglement of this state is actually lower bounded by a constant for all d. So it doesn't go to 0. It's lower bounded by a constant. It turns out it's also upper bounded by a different constant. So we kind of know it's asymptotically constant. We don't know the value though, but whatever it is, it doesn't go to 0. And our theorem too is exactly that this state is a good example of a gap between the Stein exponents. Okay, so this Stein exponent, turns out that we can prove that this is equal to the regularized relative entropy of entanglement. It's lower bounded by a constant. We compute it by showing that it's equal to this regularized relative entropy of entanglement, and then we piggyback on Cristandol, Schuch, Winter. And what we do is also to compute this regularized Piani, to estimate it at least, and we show that it goes to 0 when d goes to infinity. Okay. Right, so in particular, there is a gap for large enough d, because 1 goes to 0, so that the one under separable measurement, the Stein exponent under separable measurements, which I should have written here, goes to 0, but the Stein exponent with all measurements doesn't. And this shows that entanglement testing can be affected asymptotically by this restriction. And I also want to stress that this equality here, this is exactly the generalized quantum Stein's lemma for the antisymmetric state. Okay, so in this particular case, we can prove it. Okay, good. I'll just move on to the summary because I think my time's up. Okay, so I hope I convinced you that there is a profound connection between axiomatic entanglement distillation and entanglement testing, and that dually non-entangling operations, and that this correspondence go into entanglement testing with separable measurements. And this can be strictly less powerful than entanglement testing in general. And in particular, okay, we got the special proof of the GQSL for the antisymmetric state. Okay, with that, I thank you very much. I forgot to say, this is joint work with Bartosz Regula in the audience.
Thank you very much. The floor is open for questions, so please go to the mic if you have any question. If not, I'll kickstart. So is your new distillable entanglement useful for getting tighter bounds into the distillable entanglement of some families of states?
Good question. So we don't know how it compares to the other bounds. So we suspect that it's incomparable to several of the other bounds. But there are no clear relationships. So like the other two bounds that are kind of the very competitive bounds are the regularized Rains entropy and the squash entanglement, and we don't know how it compares to them. But maybe it's a bit easier to evaluate in certain cases. I don't know.
Yeah. So my question would be that usually in this kind of setup where you have this equivalence between the general kind of Stein's lemma and this reversibility of entanglement, the setup is that you have asymptotically non-entangling operations. Whereas now you've only been talking about non-entangling operations, and also
for the distillable entanglement, it doesn't matter.
It doesn't matter.
It matters only for the cost.
And so also like this thing, everything you showed for this dually non-entangling operations you could do with asymptotically.
Yeah. It works. It works in the same way for asymptotically non-entangling. So you get the distillable entanglement is the same, and the cost is also the restriction to dually non-entangling. It doesn't affect the cost. So you get the same expression that you got in the Brandau-Plano setting, which is exactly the regularized relative entropy of entanglement.
So thanks for the nice talk. I'm wondering, so you have this dually non-entangling operations and also non-entangling operations. So it's like the latter only imposes the axiom 1, whereas this one imposes 2 axioms. Just out of curiosity, what if you just impose axiom 2? Does it make any sense?
Well, but then since you are acting on states, you can I don't know the answer off the top of my head, but I'm afraid it kind of trivializes. I'm afraid because you don't say anything about the states, you just say the dual. Yeah, exactly, because you could. Yeah, sorry, just a second. I think tracing out and replacing your state with a very entangled state, this should still be a dually non-entangling thing because but not non-entangling.
A quick question: is it clear that these two axioms are independent?
Yeah, well, for example, it's clear from this because you get different distillable entanglement in the two cases. So yeah, in that case, it's kind of clear. They are very much independent. Yes. Well, I mean, like, because you see, non-entangling is just you could do any crazy measurement and then replace your state with something. While here I'm saying just you can only do separable measurements somehow on the state before acting. I don't know.
Yeah, thank you for the nice talk. I don't know if this makes sense, but if you go the other direction and you considered LOSR as a smaller set than LOCC, would you expect to get any kind of similar relationship potentially?
This is a very good question. Very good question. We actually, I don't think we know the many things about this LOSR. For example, well, okay, I guess some states will have infinite cost, because states that are not in the convex hull of maximal entangled states, you cannot prepare, I guess, because, well, okay, I don't know. I should think about it, but I would expect several states to be very difficult to prepare. But yeah, but I don't think people know a lot about this. It's a very interesting question.
If there's no more questions, then let's thank the speaker again. We will start at 2. Sorry, 4.